And I just wanted to be explicit about uh, what these lines are that you're looking at again in relation to these two uh, concepts, the first law of thermodynamics and the energy budget. So this green line, make this green. So this green line here is temperature. So this corresponds to our change in temperature. This red line in this diagram is the solar radiation. So that is going to be our energy in. And it's also on this diagram, it's over here. And then the blue line is, so almost always in this class, I'll use red for this component, but in this particular diagram, blue represents net long wave radiation loss from the Earth. So that is this component here, and or this energy out. So there's not heat capacity represented in this diagram, but you have your change in temperature, you have your energy in, and you have your energy out. And this is what causes the Earth's climate to change over thousands to millions of years or decades, but it also causes our day-night cycle and temperature. That is, I want people to kind of translate this quantitative relationship into words. So, in words, you would say something like the sun comes up in the morning and starts increasing energy in, but the Earth is emitting radiation to space, so it's losing energy. So the temperature is still going down, but eventually at some point, the energy coming in from the sun is larger than the energy leaving. And so once the energy coming in is larger than the energy leaving, you can see from this equation that if this term on the left is bigger than the right, then what's up here is a positive number. And so that means you're going to have a positive change in temperature. And so then your temperature starts increasing because you have a surplus of energy. Energy is just accumulating. And we talked about last time, the temperature is a measure of energy. It's how fast the molecules are moving. And so if you have energy accumulating, your temperature is going to go up. Then eventually the sun starts setting, it gets lower in the sky. And so it's just less of it is absorbed at the surface because the angle relative to the surface is smaller. And so eventually what happens is your energy out and energy in equal each other again. So when they equal each other, then that's zero up here. So that means your change in temperature is zero. So at this moment in time, your change in temperature is zero. And then past that point in the evening, your energy out is larger than your energy in. So that would mean that you would get a negative number up here, which would mean that your change in temperature is negative or falling. You have now a decrease in temperature. And so that's what's happening here. So we see here that the amount of energy out actually does vary with time. And it's going up. This is actually really important, that the amount of energy out varies. What does this seem to be varying with? Is it varying with energy in? Not really, but what it's varying with is the temperature. So as the Earth starts warming up, it starts emitting more energy. So energy lost is actually directly related to what the temperature is. And that becomes important. We'll talk more about this, but that becomes very important for why the Earth's temperature is fundamentally stable. That as you start increasing the temperature, it starts releasing more energy. Energy out starts increasing. And so that can end up shutting off this energy imbalance and causing the temperature to stop changing. If you're comparing, the second question was comparing the same relationship over land versus over the ocean. And everything that I just said applies equally to both the land and the ocean. The only difference is the ocean has higher heat capacity, um, basically because there's more molecules available for that energy to distribute through. Because the land, it's very difficult to get that heat very down, far down in the land. But with the ocean, it can kind of mix around, and so you have more molecules available. So it has a higher heat capacity, and so with the higher heat capacity, the temperature is going to vary less with the same amount of energy imbalances. This energy cannot be created or destroyed. So why does putting on a coat make you feel warmer? And so I'll go back to these equations, our first law of thermodynamics, and then our analogy with the energy or the financial budget of family members. And so I'm getting at one thing in particular here with this question that becomes very important for the greenhouse effect. Like why is it that this person with a coat on feels warmer than this person, even if the air is the same temperature? About the energy out is decreased when you put on a coat or a jacket. And so like thinking about the financial budget, it's kind of similar that if you're like thinking about like I want to have a bunch more money. To me, your mind goes first to the energy in or to the money in part. So if I think I want a bunch more money, I think how do I increase my income? So my first think about this, but of course you could just as easily think about saving more. So how do I decrease my expenditure? And so that's why it's important to think about this, is that there's two ways to do it. There's two ways to change temperature. You can either increase the energy coming in, or you could decrease the energy going out. So let's go back and talk a little bit more about the kind of energy that we're talking about. So we're talking more about the greenhouse effect, and in order to understand the greenhouse effect, we need to think more carefully about what kind of energy this is, because this equation applies to anything. So this would apply to the pot of water on the stove, and so there's a certain type of energy that would be going in and out in that case. But for the Earth's energy budget, the budget of the Earth, we're specifically talking about electromagnetic radiation is this type of energy that's in the numerator here. And so electromagnetic radiation, the kind that we're most familiar with is light. And we talked a little bit about that in this class. As far as we'll go in terms of the science of electromagnetic radiation is basically just saying that it's this oscillation of waves of energy. So we have a electric field and a magnetic field. That's why it's called electromagnetic radiation. But what's important for this class is that it's the only way in which energy can move through the vacuum of space. So it's the only way for the sun's energy to get to us. It moves at the speed of light, which is not surprising because light is electromagnetic radiation. And so the speed of light literally just tells you how fast electromagnetic radiation moves. And that's 3 × 10⁸ meters per second. Here's just a little animation of electric fields and magnetic fields oscillating and traveling. But as we've mentioned, the most important characteristic, especially in this class, is the wavelength of electromagnetic radiation. That's how we categorize different kinds of electromagnetic radiation. And so you'll sometimes see this labeled with this Greek letter lambda, which is up here. And it's just showing if I measure this wave from peak to trough, or from crest to trough to crest, how long is that? And that's lambda, and that tells us a lot about the properties of electromagnetic radiation. So this brings us back to this question that we talked about in the climate science overview. And this is, I got a lot of follow-up questions on this, so I think it's valuable to go over it again. So this has to do with the Stefan-Boltzmann law and Wien's law. And so kind of the starting point of this is that all objects with a temperature greater than absolute zero, which we use in the Kelvin scale as just 0 Kelvin, all objects emit some type of radiation, some amount of radiation. And by the way, radiation here, so I've dropped electromagnetic radiation, and that's just shorthand. It's just for convenience. So it's not like, oh, now I'm talking about something else. This just is referring to electromagnetic radiation, but we just don't say that every single time. So radiation means the same thing. So all objects are emitting radiation. And there's just these two important laws in climate science that tell us something about the type of radiation those objects are emitting. And that's that the Stefan-Boltzmann law tells us that warmer objects emit more radiation. So it's pretty intuitive, that the warmer something is, the more energy it's putting out. And then Wien's law is the less intuitive one, just something you have to remember, that warmer objects emit more of their radiation at shorter wavelengths than cold objects. Think about these laws as applied to this scenario where you're turning on a stove, where you start off where the stove, let's say you start off where both burners are off, and so you don't see either one, and then you turn on this left burner. And what senses could your body use to confirm both Stefan-Boltzmann's law and Wien's law? And so it was essentially to confirm Stefan-Boltzmann's law, all you have to do is be standing there, because as you turn this burner on, it's going to emit more radiation, and you could maybe feel it in your face, or if you put your hand over the burner, you would be able to feel it. And so you're feeling more radiation coming from that burner and going into your hand. And what it's doing is it's changing energy in versus energy out of your hand and causing the temperature of your hand to increase. And then Wien's law is the slightly harder one. And I'll revisit the diagrams that explain that, but it's that when the stove is off, it's emitting radiation, but it's emitting radiation at a wavelength that your eyes can't see because it's too long. The wavelength is too long because the object is too cold. But then as it warms up, it starts emitting more radiation at shorter wavelengths, and some of those wavelengths of radiation we start to see with our eyes. And so then you can see the radiation from the burner on the left. So, yeah, and I'll just say this quickly, that in terms of this diagram, it's like when the burner is off, so if these are the wavelengths that we can see, just this certain part of the electromagnetic spectrum. And when the burner is off, you're sitting over here, you're infrared, so you can't see it. But then as it gets warmer and warmer, Wien's law says that we're going to start emitting more radiation at shorter and shorter wavelengths. And so the temperature moves over into the visible part of the spectrum, but not all the way over. So we're just starting to see just the longest wavelengths that our eyes can see, which are the red wavelengths. And so that's why you see red at the beginning. Okay, so here's a little test. So here's a picture with a bunch of people. This is Ohio State football. They are red is their color. So is all this red fabric really hot? I just explained to you that things that are red are hot and emitting radiation that we can see with our eyes. So is that true? And if it's not true, why not? What error am I making? So what you're seeing red here is very different than this. This is kind of red coming from charcoal. And the difference is that down here, the charcoal is emitting the color. And up here, all this red that you're seeing is not being emitted from those objects. That's solar radiation being reflected back to your eyes, that the fabric is, absorbing wavelengths of solar radiation that aren't red, but reflecting the red back to your eyes. And so like the test of this would be if you were to shut off the lights, or if it was to be nighttime, would you see this red anymore? No, you would not, because you're taking away the sun. You're taking away the source of that light that your eyes are seeing. Where in this case, if you shut off the lights with the charcoal, you would see it exactly the same, because that energy is coming from those objects. It's not coming from artificial light. It's not coming from the sun, and so it wouldn't change. It wouldn't change what your eyes are seeing there. So this Wien's law only applies to energy, emitted from the object itself. So putting the Earth and sun on here, the Earth is colder than the sun, and it emits radiation like the stove that's turned off at a wavelength that is too long for our eyes to see. Whereas the sun is much hotter and emits radiation at wavelengths that our eyes can see. And it's an interesting thing about the color in this case is they're just labels that our brain are giving different wavelengths of radiation. And so in some sense, color doesn't really exist except for in your mind. And there's even, speculation that like bats, bats don't see with their eyes, they see with echolocation, where they're sending off little sound waves and it's coming back to their ears, and they're making a three-dimensional picture of their surroundings from sound waves that they are creating. And there's speculation that they could see that in color, right? So depending on how the sound wave bounces back to their ears and then their brain creates a picture of their surroundings, that very well could be, they could use color the same way that we use color. And so it's not really that color is tied intrinsically to different wavelengths of electromagnetic radiation. That's something that our brain is doing, that's labeling these different wavelengths. So it's kind of arbitrary, red and orange and yellow and green. Okay, so why is this so important that the sun and the earth emit different wavelengths of radiation? So it's all in the name of thinking about the greenhouse effect. So going back to our diagram and our common greenhouse gases, we talked most about CO2, but water vapor is a greenhouse gas as well. And methane and nitrous oxide and ozone are other important greenhouse gases. And we talked about the very definition of a greenhouse gas has to do with this difference of how these molecules interact with different wavelengths of radiation. And our definition was that molecules that interact very little with shortwave radiation, so they let the shortwave radiation in from the sun, but they absorb and re-emit long-wave radiation. Those are molecules that are what we call greenhouse gases. And so then they're going to keep the Earth warmer than they would be otherwise by inhibiting energy out. It's like putting on a coat on top of the Earth, because they're going to selectively let in the energy and they are not going to let out the energy out. And so if you increase those, then you would increase temperature. So like with a coat, a coat's a little bit different in the sense that the energy in for your body is coming in through your mouth. You're eating food and then your body is burning those calories to generate the energy in. And then you're inhibiting energy out by putting on a coat, by keeping that heat inside your body. With greenhouse gases, the concept's a little bit different because these are letting in energy in from the sun, the shortwave radiation, and not letting out the energy out from the Earth, the long-wave radiation. And we could go into more details about precisely why they do this, and that's, of course, an entire field of science. Why would a molecule not interact with shortwave radiation? Why would it interact much more with long-wave radiation? And we're just gonna skip that, basically. So we're just gonna tell you that they have these properties. Okay, so I'm gonna show you a quick demonstration of this effect in a lab. One of the core components of science is experimentation. We often think of the columns of science as being theory, observation, and experimentation. And so we, in climate science, the effects that we're talking about with greenhouse gases interacting with short and long wave radiation differently, this was first discovered a long, long time ago. So it was actually in the 1860s by this person, John Tyndall, published the first research showing these properties of greenhouse gases. And so this is a little diagram of his apparatus of basically trying to shine different wavelengths of light through a tube and putting different gases in between a kind of receiver and what it's looking through to see how those gases interact differently with different wavelengths of radiation. So here's a video that is of poor quality visually, but it's a nice clean experiment to show this. I think I've shared my computer audio. Can you hear this?
How carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera, which is purring away here. A candle.
Okay, I'll just start over here. So he's gonna show an experiment. He says he has a heat-sensing infrared camera. So it's a camera, but it's not a regular camera. It's a camera that's only gonna see long wavelength radiation. And then he has a tube, and he has a candle.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera, which is purring away here. A candle, this glass tube, which is hooked up to this rather large canister of carbon dioxide gas. Now, if I light the candle, you'll see that on the monitor, the camera picks up the flame perfectly. Look at that. The hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide. Just keep your eye on the flame. The gas is invisible, so you don't see it fill in the tube. But as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat. The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube.
Okay, so this shows why scientists are kind of so sure that increasing greenhouse gases in the atmosphere should cause the Earth to get warmer. And so it's not like some correlation causation conundrum where we're seeing, okay, the Earth is getting warmer and oh, CO2 has gone up. Like maybe the CO2 going up has caused the Earth to get warmer. Like the relationship is way stronger than that because you can just demonstrate it physically in an experiment like this. And so just to show you what's going on is when you have the camera that's seeing infrared radiation and you have the candle, which is emitting visible radiation that you can see with your eyes, right? You can see the candle, but it's also emitting infrared radiation at these longer wavelengths. And then you put CO2 in between the camera and the candle disappears from the perspective of the camera because that CO2 is absorbing and it's re-emitting that radiation. It re-emits it kind of in all directions. But you know, the fact that when we're standing away from the tube and looking at the tube, we don't see the CO2 go in there, right? Because it's invisible. It lets the shortwave radiation pass through. So we're not going to see it with our eyes. But the infrared camera is going to detect that as the candle essentially disappearing and blocking that long wave radiation. So that essentially means that, you know, it would just be, you know, almost unimaginable that increasing CO2 levels in our atmosphere would not cause temperature to increase. And so that's a, you know, that would be there'd be a huge burden on someone to try to explain how it would be possible to increase CO2 levels and for global temperature not to increase. It's just this very basic, fundamental physical relationship, and is something that's just demonstrable in a laboratory setting.